Okay, Chemistry 3101. This is where we left off last time, was what we call designating R versus S configurations. So section 5.3. Now, the concept that we really kind of left off on the last class was the idea of enantiomers, right? We said non-superimposable mirror images, like your right hand and your left hand. If you put them up, they're mirror images. However, they are not superimposable, right? You can't put your left hand in a right-handed glove. Well, if I look at these two compounds here, okay, we can clearly see that these two compounds are enantiomers. How do I know that? Well, if I just look at the first compound, I see that it has a chiral center, right? That carbon is attached to 4 different groups, isn't it? It's got a hydrogen going in the back, it's got a chlorine, it's got a methyl group, and it's got an ethyl group over here. So 4 different groups. So it's for sure that we have a chiral center in there. There's only one. It's this carbon right here. And we talked about how to draw an enantiomer. You could either try to go through the labor of actually drawing a mirror image, or you could simply flip anything that's a wedge to a dash and anything that's a dash to a wedge. So since we have a wedge right here, all we have to do is redraw the molecule and we flip that to a dash and we've got the enantiomer. Now, if I was to go back to chapter 4 with you and I said, hey, I want you to name this molecule, if I didn't indicate any stereochemistry, which I didn't because we didn't learn it in chapter 4. And if you had said this is 2-chlorobutane, I would have given you 100%. I would have said that's perfectly correct. There's nothing wrong with that name at all, right? But now that we've got into chapter 5, you know that since we have a stereocenter, there's got to be some way for me to differentiate between these two. And the way that we do that is we use what's called the Conn-Ingold Prelog system. Sometimes the book uses a shorthand, the CIP, Conn-Ingold Prelog system, to donate each chiral center as having an R or an S configuration. So if a compound has the R configuration at a chirality center, its enantiomer is going to have the S configuration. If a compound is S, its enantiomer is going to be R. Now, how do we designate these two chiral centers as being R or S? How do we do that? Well, let's take a look at the rules, okay? The first thing that we do is we use atomic numbers to prioritize the 4 groups that are attached to the chirality center. So we list them in order of priority based on their atomic number. Where do you get the atomic number from? You get it from the periodic table, right? Now, I'm sure you have chunks, even if you don't know it, I'm pretty confident that most of you have chunks of the periodic table memorized. You know the second period, you know boron, carbon, nitrogen, oxygen, fluorine, right? Those are atoms that come up all the time. You know the halogens go down the group, fluorine, chlorine, bromine, and iodine. And so the higher the atomic number, the higher the priority of the atom. Then what you do is you arrange the molecule. So you manipulate it in some way on paper or in your mind. Either way works. Or if you have a handheld model and you just flip it in your hand, okay? You arrange the molecule in space so that the lowest priority group, which would be the 4th priority, right? Number 1's the highest, 4 will be the lowest priority. It's facing away from you. So oftentimes it'll be a dash, right? Because it's going back into the page or back into the screen. All right. Then you count the group priorities of the other 3 groups, 1 to 2 to 3, okay, going around the chiral center. And if it's going in a clockwise direction, we say that it's R, right? Because it's going to the right. And if it's going counterclockwise like this, we say it's S or sinister, which means it's going to the left. And it says here a handheld model can be really helpful for these. A lot of students don't need them, and there's nothing wrong with that, but they can be really handy. Well, with that in mind, let's go back to this slide here and see if we can designate the chirality at these chiral centers as being R or S. So let me show you how to do it. And we're going to start with this molecule right here. So I'm going to go all the way over to a blank document here. Just give me a second. And I'm going to redraw the molecule on our old blank page here. So we'll start like this, okay? And then we've got the chlorine, which is on a wedge like that. Okay, so on our chiral center, which again is this carbon right here, there's something that's not drawn, and that is the hydrogen that's going in the back, like this. Well, if you look at what's attached to the carbon, I'll label it in red. You've got a carbon over here, you've got a carbon here, you've got a chlorine up here, and a hydrogen here. Well, which one of those has the highest atomic number? If you look at the periodic table, it's chlorine that has the highest atomic number, so it's going to have the highest priority. Now, if you go over to your periodic table, you'll see that hydrogen is the first element. So if you ever have a hydrogen attached to your chiral center, it is always going to be the fourth group. It's always going to be the lowest priority, right? Because it has the lowest atomic number. It's only got one proton in the nucleus. Now, when we get to these two carbons, this is where it gets tricky, right? Because a carbon is a carbon, right? These two carbons, I mean, carbon is carbon. So how do I differentiate between these two? Well, the way that you do it is you look at what's connected to the carbon going away from the carbon. Okay, so if I'm going farther away from the chiral center, I have 1, 2, 3 bonds to hydrogen like that. So I'll make what I call a laundry list. So I have hydrogen, hydrogen, hydrogen. If I look at what this carbon is attached to going away from the chiral center, right, not going back in this direction, but going away from it, it's attached to 2 hydrogens, and it's attached to this carbon, right? It's going to be attached to 3 atoms going away from the chiral center. So I list them in order of atomic number. Carbon is highest, and then hydrogen is the lowest. So I looked for the first point of difference, and I see that it's right here. The carbon has a higher atomic number than hydrogen, and so this group is going to be the second highest priority. So I put a number 2 right here, and then I put a number 3 right here. Remember, this is our chiral center. We're going to go from 1 to 2 to 3, and we're going to be going around that chiral center. So I'm going to get a green highlighter, and we're going to go from 1 to 2 to 3, right? We're going in that direction. I mean, I could do it with a green pen too and just go from 1 to 2 to 3 like that. Are we going clockwise or counterclockwise? We are going clockwise, and since it's clockwise and the lowest priority group is in the back, that means that this stereocenter is R, right? We're going to the right, okay? Now, if I do the other one a little bit quicker, okay, I'll do it a little bit faster, but I'll just prove that it's S, okay? We have the chlorine going in the back like this. And let me show you a quick rule, okay? A very quick rule that you're going to employ all the time in this class, okay? We've already agreed that chlorine is the highest priority, hydrogen is the lowest priority, the ethyl group is second, and the methyl group is third. Now, here's another rule that does come up in our notes, but I want to get it out of the way quickly because I think it's really important. Whenever the lowest priority group is facing towards you, right? Facing towards you is the opposite of facing behind you, right? Whenever it's facing towards you, you determine whether it's R or S or whether it's going clockwise or counterclockwise, and then you take the reverse of that. Let me show you what I mean. So if we go from 1 to 2 to 3, right, we're going clockwise again, but since the lowest priority group is facing towards us, we reverse it. So it's not R, it is in fact S. Okay, and that's my quick and dirty approach to showing you how to apply the Kahn-Ingold pre-log rule. So let's go back to our slides here. All right, let's get back into it here. Where were we? We were somewhere around here, okay? And we applied those rules. So here's an example that's just in my slides. I think I took it out of the textbook. And this is an example where we have the hydrogen coming out towards us, right? If you look at the chiral center, it's attached to, and they made it kind of easier on this one because it's 4 different atoms. You've got chlorine, which has the highest atomic number, right? Chlorine is element number 17. Oxygen is the second highest priority. Oxygen is element number 8. Carbon is element number 6. It's the third highest. And then hydrogen is the lowest priority. But remember, we go from what? We go from 1 to 2 to 3, and we go around the chiral center. So we're going like this, which is going to the right, right? So that would be R. However, since our lowest priority group is coming out towards us, that means that this would be an S stereocenter. Now, there are other ways of, evaluating this, okay? There's a whole bunch of and they're not tricks, they're just strategies that you can take for determining whether a chiral center is R or S. Let me show you what it says you can do here. And I find this is a little more difficult than the way I just showed you. It says you can arrange the molecule, which means you can flip the model. If you have a model, you can switch it on paper, okay? So what you can do is it says, if you have the hydrogen or the lowest priority group coming out towards you, what you can do is rotate the molecule, right? So what he did, or he just took an axis and rotated it here, okay, 180 degrees to put the hydrogen behind like that. And then if you go from 1 to 2 to 3, you're going counterclockwise, which is S, which is what the molecule is. However, I think it's just easy to leave it the way it is, you know, just leave it how it is without flipping it around. You're guaranteed to not make any mistakes in manipulation. And then you just reverse the sign. But this way works too. Okay, there we go. So again, clockwise is R, counterclockwise is S. All right, and again, since the lowest priority group is coming out towards us, again, I'm repeating myself here. Okay, I'm going like this, which is R, but since the lowest priority group is coming out towards us, it is S. Okay, like that. And we usually, if you look at a textbook, like if you go pick up any textbook about organic chemistry, you'll find that the R and S are always italicized like that. I don't expect you to italicize it when you're writing it down, but we oftentimes put it in brackets like this too, because that's how we denote it in nomenclature, which we're going to take a look at in just a second. Other ways that you can manipulate the molecule, you know, there are other ways. If you're the kind of person who likes to Google, you know, everything that we do, you know, and look up, you know, a second opinion, or look up just, you know, maybe you have another organic chemistry textbook that you've seen somewhere that you really enjoy. I find that rotating the molecule leads to errors. So I don't recommend it. I just recommend, you know, reversing the final configuration, but that's something that you'll have to determine on your own, which way you want to do it. You know, what's important in science is getting the right answer, right? You just want to have the correct answer. But again, I don't recommend rotating it, and I won't do it a whole lot when we're looking at examples. So I showed you how to make what I call the laundry list, right? So the times when we have to make the laundry list are usually when we have a carbon atom attached to the chiral center, right? And this is just showing the same strategy that I showed you already, right? Oxygen has the highest priority. Okay, it's got the highest atomic number. Hydrogen has the lowest priority. Well, I have a carbon here and I have a carbon here. So remember, you go away from the chiral center. Okay, what's this carbon attached to? It's got two hydrogens, right? And then it's attached to this carbon. So CHH, which we have here. And then here, this one is also attached to CHH. So this doesn't work. Like we didn't break the tie yet. It's a tie. So what do you do when you run into a tie? You go to the next carbon. You just keep moving on down the line. So on the left-hand side of the molecule, I'd move to this carbon. On the right-hand side of the molecule, I'd move to this carbon, right? So what's this carbon attached to? And I know you can see it on your slide if you have it printed out, but it's attached to a carbon, and a hydrogen. So we'll put CCH. And this one is attached to a carbon, a hydrogen, and a hydrogen, right? So it's attached to CHH. Well, there's your tiebreaker right there, right? You can see that carbon has a higher atomic number than hydrogen. So this must be the second highest priority group over here. And you can see the answer is right here, okay? There you go. So the sec-butyl group has a higher priority. Well, let's figure out, is this R or S? Could anybody answer that for me? And it's this stereocenter right here, and it's not a trick question. Would this stereocenter highlighted in yellow, would that be S or R based on what we've seen? Yeah, I think my students have the right answer. Let's check. Okay, they're saying, okay, Mr. Dion, you go from 1 to 2 to 3, right? You're going this way, which is counterclockwise, which would be S. However, the lowest priority group is coming out towards you, and so this stereocenter would be R. So the answer is R for this one. All right, and we're going to get some practice on that. Okay, let's see here. So the priority is based on the first point of difference. I haven't seen a student really try to, you know, add numbers up or anything like that. But just to, you know, reiterate, it's about the first point of difference, right? When we have a tie, right? You can see you got a carbon here and a carbon here, so that's a tie. So what are they connected to? Oxygen, hydrogen, hydrogen, and carbon, carbon, carbon. So oxygen is the winner. Okay, it's got nothing to do with tallying up numbers or anything complicated like that. We try to make it as simple as possible, right? What if you run into a double bond or a triple bond? Well, let me show you what you would do then. When prioritizing using the Kahn-Ingold-Prelog rules, the double bonds count as 2 single bonds. Okay, so this chiral center here, that's kind of a fun problem. Something else, well, let me just answer this part first, okay? So this carbon here is attached to, you know, carbon, hydrogen, hydrogen. This one's attached to carbon, hydrogen, hydrogen. This one's attached to hydrogen, hydrogen, hydrogen. Okay. But this one here, if I zoom in on it, this carbon has 2 bonds to oxygen. So each bond counts as a single bond. So it's attached to oxygen for the first one, oxygen for the second one, and then hydrogen, right? And you list them in order of atomic number, starting with the highest, right, and then going down to the lowest. Okay, so there you go. So let's say you had, you know, let's say you had a carbon. Let's see. Let's say you had a carbon like this. That you had a methyl, and then you have. Let me see here. I'm trying to think of an example off the top of my head. If you had something like this, and then an ethyl group here, then you had a propyl group like this, and then if you had this guy like this, if you have a triple bond, right, what is this carbon attached to? This one right here, it's attached to carbon, carbon, because carbon, 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 right, because there's a carbon here. Okay, so that's the way you would treat a triple bond. All right, there you go. So that's the Kahn-Ingold pre-log rules. Another rule, okay, well, there's a couple more things you have to look at. So it says here that handheld models, I'm just reading straight off the slide, can be really helpful when you're trying to manipulate the molecule in space so that you put the lowest priority group facing away from you. Other tricks that you can use, this is a funny one here that always makes me laugh. Switching 2 groups on a chirality center will produce the opposite configuration. So if you flip any two atoms, if you mix them up, like swap places, you go from S to R or R to S 100% of the time. Also, if you flip 2, and it doesn't even say that in here, but if you flip 2, right, if you flip these 2 and then these 2, you end up with the same. Okay, you'd end up with S whenever you flip 2 atoms and then 2 atoms again. Anyhow, that's neither here nor there. All right, so here's the Kahn-Ingold pre-log rules summary. I mean, you could maybe print this out when you're practicing, or you could try to memorize it, but I can tell you right now that, you know, after a little bit of practice, you'll get the hang of it. So let's just take a quick peek at it. First step, look at the 4 atoms attached to the chirality center. You assign priorities based on atomic number. Highest atomic number gets highest priority. Lowest gets lowest priority. If 2 atoms have the same atomic number, you keep going away from the chiral center, making those laundry lists, if you will, until you find the first point of difference. And then you prioritize based on that. Step 4, I'd say take that one with a grain of salt. You can either rotate the molecule so that the lowest priority group is going behind the page, or you can just reverse the stereochemistry, depends, okay? And then the last one, if it's going clockwise, it's R. If it's counterclockwise, it's S. And that's it, my friends. Let's take a look at a problem here. So this is comes from the book. I don't know if anybody recognizes this molecule. It's called L-Dopa. So anyhow, and probably some of you have heard of dopamine before. Anyhow, so this is L-Dopa. Could anybody assign, or I'll give you a few seconds to think about, you know, would this chiral center be R or S? And don't look at the answer, you know. Give it the old college try. I'll give you a few seconds if anybody's got a answer. Yeah, Parkinson's drug. There's a really interesting documentary about L-Dopa, and you know how they were giving Parkinson's patients like tons of L-Dopa. It was made in the 1980s or 1990s or something on the TV show Nova. If anybody thinks they have it, just throw it in the chat, or you could unmute your mic, take a class vote on it. Does anybody have an idea? Maybe I can't see what you're typing. Let me double check here. Right. I'll give you another second or two to see if you can come up with an answer. All right, we got a split here. You know, some people say R, some people say S. Well, let's double check. So there's one chiral center in the molecule. It's this one here. Okay. I like to when I'm doing stereochemistry, I like to write the atoms that are missing, you know, the hydrogen. So I'll put it out here like this. We know that hydrogen is the lowest priority group. If we look at what's attached to the carbon, if I just write it in blue, we've got a nitrogen, we've got a carbon here, we've got a carbon here, but we've got a nitrogen there. Well, boy, nitrogen has a higher atomic number than carbon. So the nitrogen is going to be group number 1. Then if we make the laundry list, what I call the laundry list for this carbon is attached to oxygen, oxygen, hydrogen. Sorry, oxygen, oxygen, oxygen is what I meant to say. We move that over a little bit here. And then this carbon is attached to carbon, hydrogen, hydrogen. And so this would be the tiebreaker. That means that the carboxyl group will be the second highest priority, like that. And then this group over here would be the third highest priority. So let's see, we go from 1, I'll use the black pen. We go from 1 to 2 to 3, which would be clockwise, which would be R. But since the lowest priority group is coming out towards us, we reverse it. And the stereochemistry is S, Sinasta. Okay, so this is an S compound. Yeah, because the hydrogen is coming forward, we have to reverse it at the end. So there you go. Yeah, that's your, introduction to, determining stereochemistry, R and S. And I think you nailed it. All right, there we go. So the R or S in nomenclature, how do we use it? So we put it right before the name of the compound. And again, we use that to distinguish compounds that are enantiomers or other types of stereoisomers that we'll look at today. So here we have R2-butanol and S2-butanol, and eventually you'll get quicker at it. Another little trick that I'll tell you is that when you look at R groups that are linear, like these, right? Ethyl, methyl, so methyl, ethyl, propyl, butyl, pentyl, hexyl, heptyl, right? The longer the carbon chain, the higher the priority. Okay, so since ethyl is longer, you know that this is going to be number 1, this would be 2, this would be 3, and the hydrogen's in the back. So, right, it's going to be R like that. Okay, another one is if two groups are isomeric, like let's say you had, in terms of the number of carbons, let's say you had a propyl over here. So 1, 2, 3, and then here you have an isopropyl like that. The one that has more branching on it, if they have the same number of carbons, is going to be higher priority. Okay, so this would be 1, this would be 2, this would be 3, like that. So that would be S. Okay, that's just another little quick trick that I could show you, but that's something that I found in my travels teaching organic chemistry, that students will usually pick up on that one. Okay, they're like, yeah, I kind of figured that out, right? This group, like if you look at the 2R, 3S, 3-methyl-2-pentanol, right? This is the second, this is stereocenter 2, so they're saying that it's R. Well, this is highest priority. Since this is a bigger R group, and you can tell it's got branching here, you know immediately that's going to be the second, and this will be the third. So that's clockwise. So yes, it is R. So that all checks out. Then if you look at the second stereocenter, you've got the hydrogen coming out in front. You know that this is going to be your first, this is going to be your second, this will be your third. So you go from 1 to 2, 3, which is R, but the hydrogen's coming out, so you reverse it. It's S. Now that was pretty quick in terms of evaluating it, but what you're going to find is that the more practice you do, you'll be just as fast or faster than me at it, okay? It's just one of those things that takes practice and looking at it over and over and over. Well, this is something that I elucidated to or mentioned briefly before we started recording this morning, is that since the structures of enantiomers only differ in the way your right hand differs from your left, that means they're going to pack the same way, right? Think about it. If I have Avogadro's number of R carbone molecules, they're going to pack the same way as if I had Avogadro's number or 1 mole of S carbone molecules. So the packing or the interaction between molecules is what governs their physical properties, doesn't it? So they're going to have the same physical properties. What does that mean? You can't differentiate between enantiomers using melting or boiling points or refractive indices or densities. It's not going to work, okay? So enantiomers only differ in how they're going to interact with other chiral compounds, which is not really discussed in our level organic chemistry textbook. If you decide to take organic chemistry for chemistry majors, that's covered in that class a little bit. but we are going to talk about their optical activity. Okay, what optical activity is. And there's a really cool way that we can differentiate between enantiomers. Let me show you what it is. So if you just think about regular light, okay, if we just shine a regular wavelength of light, doesn't matter what it is, could be white light, it could be red light, it could be a blue light, it could be ultraviolet light, whatever. But if we look at the travel of light waves through space, we see that the light is going to scatter, or the wavelengths of light, I should say, will be in all directions perpendicular to the travel of plane, right? You see that we have these arrows going in all these different directions. Well, what you can do is you can pass the light through a polarizing filter. Now, I've kind of given up on asking this question because I don't know why, but when I was a teenager, a big thing was polarized sunglasses. And if any of you have ever seen, and I don't own an expensive pair of sunglasses, but you don't have to spend a lot of money to buy polarized sunglasses. But polarized sunglasses sometimes will come with a tag attached to the sunglasses when they're in the store, and you can put the tag, which has a little lens on it, in front of the main lens on the the sunglasses, and you can rotate that lens, and what it will do is it will block out light completely. And the reason why they put that tag on there is to let you know that you're buying real polarized sunglasses. And what the polarizing filter in the sunglasses do is they cancel out all of the light except for the light that's going in one direction. So that's what a polarizing filter is. Okay, this is a polarizing filter. I'm just going to go for it. Has anybody ever seen sunglasses like that in the store that has a little hang tag on it? One of my students told me that the Oakleys sometimes have it. I can't afford a pair of Oakleys or anything like that. My sunglasses literally cost $2.99. But has anybody ever seen this before? Polarized sunglasses with the tag? Maybe if you buy a pair of Coco Chanel's or something, I don't know. Anyhow, okay, maybe nobody's ever seen it before, but that's what a polarizing filter is, okay? It only allows one direction of the light to go through, okay? So what happens, again, if you take that little polarizing filter that comes on the tag of polarized sunglasses, okay, and again, you just throw it in the trash after you buy the sunglasses, it's just proof that you're paying for, you're getting what you're paying for. If you rotate it in a perpendicular to the first polarizing filter, it cancels out all the light. So what happens is you rotate that lens, you get no light passing through. Okay, so that's just the whole concept of plane polarized light. So what happens is this, check this out. It says when plane polarized light is passed through a sample of a chiral compound, right, like one enantiomer, okay, what happens is that the plane of that light is going to start to, it's going to rotate in one direction. Okay, and if you remember what I told you before I started recording this morning, is that one enantiomer is going to rotate the plane polarized light to one side in one direction, and the other enantiomer will rotate it the exact same amount, but in the opposite direction. Okay, this is kind of cool when you think about it. Now, if you're wondering, and I wondered this the first time I heard this, how do you shine it through a molecule? What do you do? Like hold up the molecule with your hand and put a beam of light through it? No, of course not. Okay, what you do is you actually make a solution, and I'll talk about that in a second. But anyhow, compounds that rotate plane polarized light, so like one enantiomer isolated, we call those compounds optically active. Okay, so a compound, again, that rotates plane polarized light, we call it an optically active compound. The only time you're going to have a compound that can rotate plane polarized light is something that's going to be optically active, right? Let's say you take and you make a solution of hexane, 1, 2, 3, 4, 5, 6, right? You put hexane in a solution and you shine plane polarized light through it. It doesn't do diddly squat. Why? Because there's no chiral centers in hexane. Okay, you have to have an optically active compound. You've got to have a chiral compound in order for this to happen. So this is kind of our textbooks, hammer and tongs approach to explaining what a polarimeter looks like. A polarimeter, we actually have one at UCCS in the undergraduate lab. It looks just like a big long metal box, okay? But the idea is this, is that you have your light source, which is usually a sodium lamp, okay? It's actually always a sodium lamp. So the wavelength of the light, I think, is 589 nanometers. It's the D line of sodium, which is neither here nor there for this class. But anyhow, you shine one wavelength, you pass it through the polarizing filter, so then you just get one direction. See, that's this right here. You've got one direction or one wavelength of light or sorry, one oscillation of the wavelength of light, I should say, that's goes through the polarizing filter that comes through. And then in the polarimeter tube, this is where you have your organic molecule. Okay, so let's say you have an organic molecule like, you know, our 2-chlorobutane. Okay, well, what you actually do is you take it and you make a solution of it in something that's, you know, not optically active, just a solvent like maybe dichloromethane or something like that. And then you shine the light through it. And what happens is when the light beams hit a chiral compound, again, they interact with it, and it's going to rotate the plane polarized light to one side or the other. So then you analyze it on this side over here, and you can rotate this lens, you know, to the positive side or to the negative side, and there you go. And then you just measure optical rotation. So the first time I heard this, I thought, well, there must be some kind of, you know, correlation between R and rotation to one side and S and rotation to the other side. Okay, so let me put a big disclaimer. It has nothing to do with whether the compound is R or S, whether it rotates it in the positive direction, which would be clockwise rather, or in the negative direction, which would be counterclockwise. There's no correlation whatsoever. So here's a couple of, you know, tidbits that I need you to know. So enantiomers, like I said, are going to rotate plane polarized light to equal degrees, but in opposite directions. I can tell you right now that a couple of years ago, there was a question on an ACS final exam, and I don't have the exam in my possession, but I have a little bit of it in my memory, okay? And one of the questions was nothing more than this. It says, you have a chiral compound. It rotates plane polarized light, and you measure the optical rotation, and it's positive 90.1 degrees. What will be, you know, the optical rotation of the enantiomer? What's the answer? The answer would be negative 90.1 degrees, right? All this question was asking is, do students know this? Same amount, but opposite directions for enantiomers. That's all the question was asking, nothing more than that. The amount of rotation of the light depends on a couple of things. It depends on sample concentration and the path length of the light. Okay, so concentration is here, and path length, which is usually 1 decimeter or 10 centimeters. Anyhow, there's a whole standard procedure that we have for measuring optical rotation. It's usually 1 gram of compound and 1 milliliter of solution. I'm never going to ask you about that. Okay, I'm never going to ask you. And if you're wondering, like, can you summarize what you're not going to ask me? Yes, I have it summarized on a slide in a second. But I'm not going to ask you to do any calculations at all. I know that there are a couple of questions in the textbook, our textbook, that ask you about calculations using this formula. I will not ask them. They will not be on your final exam. They will not be on your quiz. I did not put them in the list of suggested problems. However, it's handy to know that the optical rotation is the angle. We put that in here in square brackets. This number up here is the temperature. We usually measure everything at 20 degrees Celsius, so it's usually just a 20. And then the wavelength, like I told you, it's 589 nanometers, which is the D line of sodium. So we usually just put a D here like that. We use a sodium lamp. Anyhow, so again, let's say you have R and S 2-bromobutane. If one of them rotates the plane polarized light, remember we use the D line of sodium, we're at 20 degrees Celsius. If it rotates it at negative 23.1, that means the enantiomer is going to rotate it positive 23.1. Okay? So R and S, again, refer to the configuration at the chirality center. And positive and negative, those refer to the direction that the plane polarized light is rotated. So when it rotates it in the positive direction, we call that dextrorotatory. That's clockwise. Okay, so this is clockwise, and this is the rotation of light. This is not R and S. Okay, and levorotatory means it's rotating counterclockwise or to the negative direction. All right. So also something else that's important that you understand or that you just know is that optical rotation depends not only on the path length of the sample and the concentration, it also depends on the temperature. Check this out. Are you ready to have your mind blown a little bit? This is crazy. Okay, you have this compound here. It's got the S stereochemical configuration here. We could double check that. We get the hydrogen over here. That's lowest priority. We have the nitrogen, which is number 1. This is going to be number 2. This will be number 3. So we go from 1 to 2 to 3. There you go. It's S, so it looks good. Anyhow, check this out. This compound is levorotatory or negative at 20 degrees Celsius, but you crank up the heat and all of a sudden it's positive. So there is the optical rotation changes with a lot of things, okay? Concentration, path length, temperature. And so we have to be really careful when we take measurements with optical rotation. Okay, so one thing that you got to get through your mind, and usually students will know this as soon as I tell them, but there's no correlation between RNS and levorotatory and dextrorotatory, plus and minus, okay? There's no correlation between the two. Zilch. They do not correlate in any way, shape, or form. So if you know that the stereo center is S, there's no way you can make a prediction. And a good question, would be, hey, let's say I have a bunch of, amino acids or something, or a bunch of compounds that are closely related, right? I think a good question would be to say, like, hey, well, if one of them rotates plane polarized light, in the positive direction, if I have something and I just change it slightly, is it going to be, is it going to rotate it in the same direction? The answer is you don't know. There's no way to predict. Okay, you actually have to make the measurement. I know this because I've lived it when I was in graduate school. Anyhow, so the magnitude of optical rotation can't be predicted. You got to measure it. So, there's the saying, ain't no way but the hard way, right? You literally have to step into the lab, put on your lab coat, weigh out the sample, put it in the polarimeter. You have to warm up the polarimeter to get the lamp, warmed up or whatever, but you have to physically go into a lab and measure it, which is kind of cool. Anyhow, however, there are some predictions we can make about optical rotation. I have a question for you. The answer's on here. I was going to ask you, what do you think a racemic mixture would do? Well, a racemic mixture is a 50-50 mixture of two enantiomers. Okay, a 50-50 mixture. So that means you've got 50% R and you've got 50% S. Well, if we go back to what I told you a few minutes ago, that R and S are going to rotate plane polarized light in the same amount, but in opposite directions. I showed you here, and I gave you another example here. Well, what do you think that's going to happen if you have a 50-50 mixture of one that rotates plane polarized light in one direction, and the other one rotates it in the opposite direction? They cancel each other out, okay? So if you have a racemic mixture, again, which is an equal mixture of R and S, okay, they cancel each other out, all right? Anyhow, but if one is present in excess, like let's say you had a 60-40 mixture, then there's going to be an optical rotation, but less than the pure enantiomer. We call that enantiomeric excess. I'm never going to ask you to calculate enantiomeric excess. There's a calculation you can do, which is shown here, but I'm not going to ask you any questions about calculating enantiomeric excess, okay? So what's the summary? Students always want to know, like, what, give it to me straight, Mr. Dion. What do I need to know? So these are the main concepts that you need to know from section 5.4. And this would be the same if you were in Dr. Anderson's class. We maintain continuity throughout the chemistry department at UCCS. So you need to understand the idea of plane polarized light, right? We talked about that quite a bit. And what a polarimeter does, right? You make the sample, you shine the light through it, it rotates the plane polarized light, you measure it. I'm never going to ask you to do a calculation about a specific rotation, okay? I'm never going to ask you to calculate an enantiomeric excess. Not going to ask you to do that. But you should know what the concept of optically pure means. That means you have one pure enantiomer by itself, nothing else, okay? Enantiomeric excess, that means you've got one enantiomer in a greater amount than another. And then a racemic mixture is a 50-50 mixture. And these are terms, optically pure, enantiomeric excess, racemic mixture, these come up all the time in organic chemistry, especially racemic mixture, right? Like, so let me show you something about racemic mixture. You remember that, I don't remember exactly. Yeah, it was 2-chlorobutane, right? Back in chapter 4, remember, and we're going right back to where I started with this section. If you had called this 2-chlorobutane, because we hadn't learned about chirality yet, and there's nothing wrong with that name when you're not provided any information. Well, me as an organic chemist and you as an organic chemistry student, if you ever see a molecule drawn like this in the textbook, where you're like, hey, wait a second, that's a chiral center, but it doesn't show if it's if the bond is coming up or down. They don't give me any information. You can make the assumption from now on that whenever you see a chiral center but it's not identified, you can make the assumption that it's racemic. Okay, it's a 50-50 mixture. All right, there we go. All right, another funny example about racemic mixtures is, you remember last class we were looking at some prescription drugs, small molecules by sales, and one of them was Omeprazole, which is sold as Losec by AstraZeneca. Well, what's interesting about that drug is it was originally sold as a racemic mixture, a 50-50 mixture of R and S. And I don't remember exactly which stereoisomer had the therapeutic effect, but let's imagine that it was the R that had the therapeutic effect. That means it, caused the, whatever it is, acid reflux to go away. But this one had no effect. Okay, it didn't have any deleterious effects. It didn't have any negative side effects. It just didn't do anything. Okay, it just got metabolized and probably came out in the urine, feces, breath, sweat, whatever. It was just metabolized and excreted from the body. Okay, so no big deal, right? Well, what's funny about that is, and you probably won't laugh when you hear the story, is that when a pharmaceutical company markets a compound, they have to patent it, and the patent life, you probably know, doesn't last forever. Now, I haven't been in the pharma industry for a few years. I'm not sure exactly how long the patents last, but at one point they lasted around 7 years, and that also depends on the country. The country, whether, and I lived in Canada, so it depends on where you are. But let's say it was 7 years. So what happens is, after 7 years, a generic company can jump in and say, you know what, I'm going to start making this myself. I'm going to start making a mixture of this, because they can figure out what the structure is, right? Once it's on the market. So they can jump in the game and start selling it, and undercutting the people who designed it and developed it and originally marketed it and sold it. So what happened is, once the patent was up, they went to court. AstraZeneca went to court, and they said, "Hey, you know what, man? We didn't know that this one had no effect. We were unaware. It was unbeknownst to us. We thought it did have a therapeutic effect." I'm not sure if they said that, but I'm pretty sure that they said, we didn't even know. We thought that one did have a therapeutic effect. So what they did is they went to court and they battled to then remarket the drug as only the single enantiomer, because the other one didn't have any effects. So you don't need it, okay? But it's a little bit more difficult to make it pure. But they said, hey, we're just going to market this, and we want to extend the patent life for another 7 years and rake in all the cash. And I think they won, okay? So it's kind of an interesting thing there. Anyhow, so chiral synthesis, making a chiral compound, making one enantiomer over another, is something that doesn't come up a ton in organic chemistry 1, but it's a lot more challenging than making racemic mixtures. Anyhow, something to think about there. Another quick story. I'm going to stop recording here. Let's see, because I don't want to post this